Good evening, everyone. First of all, I sincerely thank the 49th batch of our department, our seniors, for organizing the wonderful series of session for us. It is my great honor to introduce today's distinguished speaker. He is a proud alumni of our department from the 49th batch and currently serves as the managing director of Modelon India. Modelon is the global leader in simulation software, helping industries improve product development and operation. We are privileged that our respected alumnus has taken the time to conduct the special online session for us. So now, I warmly welcome Mr. Anand Pitchaikani, Managing Director of Modelon India. We are very happy and honored to have you with us today, sir. And also, we would also like to extend our thanks to Jay Kumar Senior for coordinate with their batchmate and organizing the session. Today, they will be going to discuss about a role of simulation in aerospace industry. Dear friends, if you have any doubts, please feel free to ask him during this session. So, thank you. Welcome, sir.
Yeah, thank you, Muthulakshmi. Yeah. So, Jay, you want to give any forward?
Um, no, I think it all started with a WhatsApp call after our reunion, right? I think we felt the college has done so much for us. How can we give back? And then during our interaction with the students, we came to know that there could be a need for a few talks about topics that are relevant to the students, be it technical, non-technical, right? So Chilean was very proactive in collecting the topics and giving to us. It made our job a bit easier, right? So thanks to Chilean and the rest of the students as well. I would request all the students to use these sessions wisely. We used to call Anand as the Tendulkar of MIT, right? So he's not seeing the match and coming and taking the session, right? So please make full use of it. Be participate well. Ask as many questions as you can, right? Make full use of the session. Right? With that, I'll pass it on to Anand.
Thanks, Jay. So, I'll just start to share my screen. Let me know when you're able to see the presentation.
I think we are seeing your
Okay,
screen, but not the presentation.
sure. I'll just change it just a moment. Is it okay now?
No, I think still we are seeing the teams.
Okay, so yeah, I think I shared probably the program on the screen. Yeah, just a moment. Yep.
Yeah, we are able to see it.
Good. Yeah. So thanks, Jay. And before I start, I would say I represent 49th batch here, and as Jay said, it is going to be series of talks. So basically, myself, Jay, and in this call, you have two more seniors from our batch. So Kannan is here, and also Arun. They also joined this meeting. Anyways, Jay has already neatly summarized. I think we want to give back something, and this is small way of doing it. And anytime during the this meeting, you can interrupt and ask me questions. And also, this is just a starting point. So pour your ideas to Chelian and see how we can develop this, or you need something more. So that is also something that we can take up. So today's topic, it is going to be role of simulations in aerospace industry, as I saw that as one of the topic of interest that came from you. So what you can expect out of this, let us say, talk is it is going to be a very broad topic. So I'm not going to go into the details. I'm not going to go into any specifics. But what I'll try to do here is kind of explain what simulation means to aerospace industry. So simulation is one word, but I think it has several meanings. So I'll try to kind of broadly capture all these. And definitely based on your interest, we can later on expand if any specific things of interest to you. So what we will do is we'll first see why simulations are important, and then product development life cycle of an aircraft, and how simulations fit into that. Then role and types of simulation. So as I said, simulation is one word, but it has many meanings. So we'll see what are all the different types of simulations. We'll see some simulation fundamentals. Again, I'll just briefly touch. So I think when we have other topics where we go into particular type of simulation, we can go into a lot of details. I'll also show some simulation tools which are in market. What are the opportunities that you have in market for simulation? And finally, what should you do, right? As a student, what should you do to kind of make your career in simulation? So that is also something that I'll try to cover. So why simulations? So there are multiple, benefits of simulation. So basically, when you look at any industry, whether it is aero or auto or any machines that people make, I think so many years ago, maybe right when the industrial revolution was on, people were heavily dependent on prototypes. So they have an idea, they prototype the idea, they test it. If it fails, again, why it fails, change, something, make another prototype, test. So that is how, things were going. So simulation was like a gift, the always the fundamentals in terms of physics and math was there. But how can we use computers to efficiently solve this? So as the computer industry also picked up, I think that is when we saw the benefits of simulation. So cost efficiency is an important thing. So as I said, so you cannot make, I mean, imagine a jet engine, right? So how many jet engine prototypes can you make, fail to, perfect a jet engine, right? So the cost of making an actual prototype, testing it, compare it with, many number of simulations that you run. Of course, the simulation has to be accurate, but once the accuracy is reached, then you kind of see the cost benefit there. Then there is also a risk reduction. So risk is again, delays in projects or when we are talking about aircrafts here, right? I mean, there is always life involved. So simulations can give a lot of benefit when it comes to risk reduction. Accelerated development. Again, typically it cuts down, let us say, the time required to go from a concept stage to an actual product. I think simulation plays a heavy role in kind of shrinking the time that it takes. So just imagine the number of, let us say, simulation is something which can keep running in your high performance computers or big nodes that you have, and the number of simulations that you can run to get an idea of, to optimize a system, or to get plot what are all the possibilities and pick what you want. So it accelerates development. Handle complex physics. So this is also something which I was talking about. I mean, physics is always there, but how do you solve complex problems? As the computing also improved, I think then we were able to handle a lot of these complex physics. So complex physics can be neatly handled through simulations. So that is an important thing. Then as I said, design optimization, right? So you can always optimize since there are design parameters are available to you, wingspan, let us take, or you take any type of aerofoils, or you take anything for that matter. So you can keep varying that. So you have 3 or 4 design parameters. So you can say, this is my design space. It can vary from this value to this value. And this is my end goal. So let us say the thrust that it produces for a jet engine is your end goal. So you can keep that, and within the design space, you can explore, right? You can run so many simulations and you can optimize. So I'm just giving an example on a jet engine, but this can be applied for anything. Then another thing that we are seeing recently is certification and compliance. So when you talk about companies like Boeing and Collins Aerospace, they heavily depend on simulations for certification. So for example, FAA, so they kind of take a lot of these simulations. When you prove that your simulations are very accurate, so you can submit a lot of your simulation reports to get your system certified. So that is also something which is upcoming, and it is used heavily. Then training and mission planning. So how do you train your pilots, right? I mean, this is also an important thing where simulation can be used. So these are broadly, I would say, for an aerospace industry to reduce cost, to make products quicker, to handle complex things, to optimize, to certify, to train pilots. So these are all the various motivation for simulations to be done in aerospace industry. So I'll talk about product development life cycle because forget about simulation. What is more important as an aeronautical engineer, where we play a role is from concept stage. Let us say tomorrow somebody comes to us and tells us like, hey, I'm interested in a 100-seater aircraft, which should be able to travel, let us say, 1,000 miles. Can you design it, right? So we have to be product focused. So everything starts with the product. We need to design the product as per requirements. We need to design it and implement it as reliable as possible, right? So we need to understand how product gets developed. So that is a core thing. And then there where simulation plays an important role, right? So let us go through this process now, try to understand what is product development life cycle. So there where actually simulation comes into picture is what something we'll see. And so here I'm just showing you a picture just to give an idea, like in terms of cost. So you can see this is the life cycle of, let us say, an aircraft, which is like 50 years, right? From the conceptual stage to, you are decommissioning your aircraft, right? So this is the full 50 years that they have plotted here. And this is like the financial gains. So the initial years, so you are always pushing in a lot of money, right? This is the R&D period where for design, for initial certification. So for everything you spend money, you are doing R&D all the time, you are perfecting your product, and then you launch your product. So your program is launched, and it takes a lot of time, more than 10 years to turn positive. And if you really look at break even, so break even happens after 20 years. So it is, we're talking about a large time scale that we're talking about. And this gives us an idea like how much money is pushed in, and anything that we can do to gain some, let us say, cost savings. So simulation basically plays an important role in this phase, and if it can reduce the cost, so you can definitely break even much faster. So that is something that we can understand from this plot. And another one is, this is just to give an idea, like any project from the time they announce to when the first flight happens. So it is on an average, they say it is 7 years. And these 7 years, lots and lots of simulations gets done, because the initial years, so you can always do simulation of an aircraft which is already flying just to perfect it or just to troubleshoot it. But maximum amount of simulations are done during these 7 years of from concept stage to when you actually realize an aircraft. So as a product, so these are the timelines, and this is the cost that involves, and this is how much time it takes to actually break even. So as a product. And this one is, so this is called as a V cycle. So for now, you can understand the cycle starts here at the top left, and you keep drilling down, you come to this point. From here, you again start moving to the right. So for now, you can keep an eye. Any question?
Anand,
Yeah.
can I ask a question?
Yes.
I first time I'm seeing this product life cycle of this aircraft here. So you say it's 7 years for to start the concept to bring it to the design or to the product. How much savings do you envisage using the simulation from what it was then when simulation was not there to what we are now with using all the simulations? I just want to have an idea.
Yeah, I would say, I mean, the answer again keeps changing around. So 20 years ago, the maturity level where we were at, we were talking about, let us say, 20%, 25% kind of numbers. And now as we mature, more and more experiments, more and more prototyping, more and more, internal testing is being replaced by simulations. So definitely it is more than that number now. And it should be around, 30%, 35%, something like that. Yeah.
All right. Okay. Thank you. Cheers.
Yeah, just an additional point here, Arun. So See, as a OEMs, they're always trying to compress the design cycle time, right? Earlier, let's say it was taking 20 years. They want to compress it to 10 years or even lesser, right? So once they lock a customer, let us say Airbus, they're going to serve that customer for the next 25 years, 30 years, right? So that's a very big business deal, right? So imagine you are able to release a product early compared to your competitor. So that is a, the cost saving is enormous there, right? So that is where simulation also plays a bigger role. In addition to reducing your prototyping cost, it also helps you to get a foothold in the market, right? By early product release. Just want to add that.
Yeah, yeah, sure, sure. Yeah, faster to the market.
Yeah, okay.
Yeah. Yep. Any other thing? Okay. Good. So as I said, this V cycle, when we look at, so everything starts with requirements. So basically, let us take a simple case. I mean, I was talking about this 100-seater. So at first, the requirement is very simple, right? I mean, it starts with so I should have a 100-seater, and range should be 1,500 miles. So those are the starting requirements. So we go to drawing board from there. So from there, what we do is it trickles down. We kind of, okay, if this has to be satisfied, then how many engines should I have? What type of engine should I have? Right. So what type of fuselage I should select? So it kind of drills down. So we start with overall requirements. We go to system requirements, and I'm just telling you, like, this is something which is very strictly followed within aerospace industry. Why? Because all these requirements, these are all documented, and these have to be traceable all through, the design cycle and certification and everything. Nowadays, they look into all of these things. So we start with aircraft requirements, then we go to system requirements. So basically, you are starting from an overall requirement and you're arriving at your system, right? So my system is like, what is my airframe? So what is my engine? So what are my environmental control system? So all these things you arrive at. Now the thing is, so it's all at an hypothesis stage. So I'm at a hypothesis stage, and I have to test this hypothesis. Will this work? Or I can give you some other example. Let us say there is an existing aircraft, and they want to electrify this aircraft, right? I mean, they want to move away from conventional jet engines to, let us say, an electric motor and propeller configuration, whether this will be feasible, right? So these feasibility studies, so it starts, we used to call this early V cycle. So this is the concept stage. So at concept stage, whatever system that I come up with, so we would like to validate that. So there we use a lot of simulations. So these simulations early that we do. So these are called as system simulation or 1D simulation that we do. We don't yet have a lot of details, but we want to quickly check whether the concept works. So this is system design part. So we do it here. So then we further drill down, right? So now we have more details. We know what kind of engine I'm going to choose. So there we are going into the actual design or the actual visualizing the actual component, right? I mean the 3D. So there even deeper simulations are done, like CFD and FEM. And once these are done, and let us say all these number of simulations, you explore the design space, you do optimization, then you finally can realize your system. Let us say your first prototype. And there is another important thing. So nowadays everything is electrified, and a lot of controls is being used, right? So the control software itself for an aircraft runs into millions of codes. So that is developed, then that needs to be combined with hardware. Then you start testing your hardware. Now from early V cycle, we come to deep. Now we move to the right hand side. So right hand side is more towards actually realizing and certifying the aircraft. So when we move in this direction, we do some hybrid simulations. So some part is hardware, some part still remains as simulation, because we don't want to waste money or because we want it to be very safe. So how do you test a controller? So typically what I do is they test the actual controller with the plant or the aircraft being inside, as a simulation model. So this can be combined and tested. So all those things we do here. So then we combine everything together. We do system integration test. So basically here, I would say there is a nice play between your hardware and your digital, let us say, simulations that you do. And strictly speaking, so we can define this as, we start with requirements capture and analysis, then we actually do the system architecture and design, then we implement it, then we verify and validation. So this verification and validation, when I talk about these 1 million lines of code that we write in controller, so everything has to be tested properly, right? The safety, the amount of paramount amount of importance that we give for safety, it has to be tested quite rigorously. So that is also something that we do, on the right hand side of this V cycle. Then finally, as I said, like certification and delivery, in fact, life cycle support throughout. How do you maintain or running a digital twin and maintaining it? So all these things are also playing a role. But the main thing that I want to convey on this slide is, so as I said, we are developing the hardware, but we can nicely see throughout this V cycle how simulation keeps playing important role. So next, we will see what are these different types of simulation, what role does it play. So this is something, so we call it as model-based systems engineering. So this happens at the early V cycle. So just to give you a quick idea, so model-based systems engineering is nothing but once you have the system picture. So can I quickly put together the system? Let us say this engine, let us say this, airframe, this kind of an environmental control system. So all these things, control surfaces, these are the different control surfaces, the hydraulic actuation systems. Once you have an idea of all these things, can I quickly put these things together and run these models? And another thing, the requirements that we write. So the requirements that comes to us, then we kind of trickle down and make the requirements larger and larger. These requirements, can they be combined together with this simulation model and checked? For example, let us say one of the requirement is the engine has to be operated, below its safety limits, and there can be pressure ratio limitation, or there can be some temperature limitation, right? Turbine exit temperatures. So all these things, when you run it through the flight envelope that you are interested in, will it really cross this temperature? Will it really cross this pressure ratio? Will it go below such certain pressure ratio? Will it surge? Will it choke? So all these questions, if you want to answer, right? So these are all available as requirements, but equivalent models are available with you, so you can quickly run these things. So this is called as model-based systems engineering, because you are doing systems development. Along with that, you are developing your models and you are checking whether your hypothesis is right or wrong. And again, here we have another V cycle for MBSE. So purely with respect to, let us say, simulations, we can understand. The earlier V cycle I showed you was for the actual product, which is in hardware, but this is purely the software part. So we start with requirements, then we come up with the design scheme, primary design. So all these places we can use system simulation. Then we go for detailed design, right? The 3D part. So there CFD, FEM, CAD, everything comes into picture. Then, as I said, integration testing of hardware and software, right? So because 3D design is done, so I will realize the actual hardware. So how I can test that with software. So hardware and loop simulation is something that I gave you an idea about. Partially hardware and partially things are in simulations. Then we integrate everything and kind of, this is the place where we talk about testing and certifying your system. Then finally everything is put onto the aircraft and there we do testing. So this V cycle is basically for the software side of things, how we develop everything. Now I'll touch about different types of simulation. So we have been talking about different things, right? The V cycle. So keep the V cycle in your mind. So we start from systems, then we kind of perfect the systems, then we go into individual components. With 3D, we can design them more complete way. Then finally we come to the right hand side where we want to run controllers along with plant models. So all these things we were talking about. Now we can give some more definition. Like so, FEM, FEA is the structure part, right? If you want to check, for example, system simulation sometimes makes a lot of assumptions, right? When you make, let us say, when you're making a very tough maneuver, system simulation always assumes that the structural integrity is always there. So it doesn't do a structural analysis and see if something breaks. So that needs to be separately done, right? So deep in the V cycle. So that is FEA or FEM that we talk about. Then CFD is mainly on the fluid dynamics side. System simulation I already talked to you about, and controls is also a part of system simulation where let us simply take the elevator operation, right? I mean, elevator is a elevator controls. So the pilot is going to fix 5 degrees, but how exactly it goes to 5 degrees, how it achieves that, someone needs to control this. So you have a controller. So this controller has to be modeled. So that is we can take that as a separate simulation. Then requirements we don't call requirements for simulation, but there is something called as requirements modeling. So you can always model requirements. So which is your bigger system? How it breaks down into simpler, subsystems. For each subsystem, what are the requirements? You can code all of these things. So there is something called a sysml. You can use sysml and code all of these things, and you can link that to either your system simulation or even CFD or FEM. It can link with, it can have link with any other, simulations. So these are the types of simulations. So requirements, as I said, you can always go from one block, and for that block, what are all the requirements that needs to be satisfied is something that you can state. And you can always, so there are some different terms, like they call certain things as refinements, certain things as derived. So for example, refinement is more like someone gives you the requirements, we directly take those requirements, we call it refined. And derived ones are, you don't directly get it as a requirement, but these are derived ones. For example, they are going to tell you like the absolute ceiling is 35,000, and the engine needs to be stable. So these are the overall requirements that comes to you, but you need to derive and say for the engine blade temperatures and other things. You have to basically drill down and come up with all these derived quantities. So all these derived requirements can be written here. So this is what we call as requirements modeling. And here we show how these requirements, for example, the formal requirement or formal specification, it's still in Word document. But from there, we can get into, let us say, the SysML kind of a structure. And these can interact with your simulation model. So here we show simulations. So for example, when your climb rate is so much, your temperatures cannot go beyond a certain level. If that is written as one requirement, you can automatically go pick the correct simulation model and put your aircraft at that climb rate and watch whether the temperature is crossing the limit. If temperature crosses the limit, it will say your design is wrong, right? So those kinds of things you can do by doing requirements and connecting requirements with simulation models. And there is lots and lots of interest on requirements modeling based on my interactions with companies like Boeing and Collins. I see them doing this in a big way. System simulation. So there is a small difference between system simulation and CFD and FEM. In system simulation, we don't consider 3D effects. We abstract everything and we consider basic equations. We don't. It's called as lumped parameter modeling. For example, aircraft dynamics, if you want to model, we consider 6 degrees of freedom. It's a rigid body, and what we study in our books, right? I mean, as equations, as differential equations. So these are modeled and these are simulated to get an idea. So we don't go for every point in an aircraft. Rather, we kind of compress the entire aircraft into a single body and model it. So that is the basic idea behind system simulation. And so here you can see system simulation is like a natural twin of these controllers. But if you want to run your aircraft in a controlled manner, so you can model your controls that I show here, and you can connect it to an aircraft and see how you can control your aircraft. So this is system simulation. Then I was also talking about, when we are discussing about this V cycle, on the right hand side, I was saying there is a place where half things are actual hardware and half of the things are simulation. So here, this is a picture taken from Airbus. So this is actually for an aircraft. you can see that they have put all the aircraft systems, for example, all the actuators, all the control surface actuators, all the different, fuel tank actuators, everything is put here. And there is no actual aircraft here, but all the systems are there. And what we can do is the actual aircraft can be run as a simulation model, and you can run any mission profile. So the actual aircraft goes through these mission profiles in computers as simulation. But these systems here, they will think as if the actual aircraft is on the air, and they will do the actual work. For example, the hydraulic actuators will move. You can see elevators, a person can sit there and actuate all the controls, and they can see for real how these controls work. So this is called as the hardware and loop simulation, or in general in aircrafts we call it as iron bird or whatever. So here also we are showing something very similar, where actuators and various heat exchangers are actual systems, but the aircraft dynamics is inside a computer as a simulation.
Anand, can I ask you a question?
Yes.
First of all, just to break the monotony, because I feel like you're talking all the way. And also, this is another genuine question. Just for the reference, me and Anand used to work for GTRE at some point in time in the distant past. So this question is related to your hardware integration. Imagine if a software like Modelon was there available in 2000, would it have increased the success rate of some of the engines that we did, or is it still the same in terms of gas turbine testing?
Yeah, so maybe it's a good question, Arun. So one thing is we are completely focusing on the simulation side of things, but I would say there are a lot of challenges on the let us say the actual manufacturing processes and other things. So, for example, when I told you when we do simulations, we assume structural integrity is there, right? So that is an assumption that we make. But when you actually realize turbine blades, which are going to rotate at, let us say, 15,000, 20,000 RPM at 1,100 degrees or 1,200 degrees, whether it will have structural integrity is something which we can only confirm by actual manufacturing processes. So I would say if you have weaknesses there, right, then simulations can't do much, right?
No, I understand. For example, remember we had this flutter issue on the blade, right? Fan blade stage 2. And we had to do it every time we had to test, and we failed, and the failure was big what you call demoralizing, right?
Yeah.
If we had done this kind of CFD integrated FEM analysis,
Yeah.
that would have at least saved the cost of failure, right? That's where I'm coming from.
Yes, definitely we save, Arun. There is no doubt about that.
And are we capable enough to do those as in GTRE?
I mean, specifically GTRE, I don't know. I'm really out of touch there.
Okay.
But when the way
It's feasible.
India has evolved, you see all these Rolls Royce, GE and others working here. Definitely, they are very successful by using simulations properly. Yeah.
All right. Okay. Cheers. Thank you, Anand.
Yeah. So, any questions from students' side so far?
எல்லாரும் தூங்கிட்டாங்க நினைக்கிறேன்.
The match. Okay. One second. Yeah. So finite element simulation, I think this is something which I would say I'm not so qualified to talk about, but still, it's more like getting the structural integrity part of the aircraft, right? Any component. For example, here they are showing that the actual aircraft is in flight and it goes through a gust. So what is the stresses and strains in various parts? And again, this is for a rotor blade. So this analysis on the bottom right that you see, it is a bird ingestion study. So in a jet engine, when a bird gets sucked during a takeoff, so how the blades get affected. It's basically something like dynamic simulation or impact simulation that you can do. So which uses finite element method to analyze So that is, finite element part. Then again, computational fluid mechanics simulation, starting from, overall external flow, analyzing the external flow on an entire aircraft, to going to specifics like, landing gear, to perfect your, landing gear design in terms of perfect aerodynamics. Or this picture is not good, but here they are analyzing inside the aircraft, inside the cabin, how the environmental control system airflow is distributed using CFD. So these are all various things that you can do using CFD. So before I go further, I will just kind of reiterate. So the system simulation part is more like, it's like bird's eye view, or, having everything put together and having the big picture. But when you do FEM and CFD, that is when you go deep into, component by component 3D and see if everything is proper. Then simulation doesn't end with, simulation. And now, as we seriously see things evolving, so simulation cannot be, boxed within whatever categorization I have done. Things are getting added a lot, and we are already, some of us are doing this. So simulation works very well together with optimization. So here there is an example where, both structural as well as CFD can be put together to get the design of a wing properly, and through simulation. So you give design parameters and design space, and it can run many iterations to get the perfect design done, where multiple tools interact together. You have FEM, CFD, and also MATLAB, working together. But finally, you will get, let us say, what is the, design parameters of interest. Similarly, we are also seeing, everyone talks about AI, but I want to be very specific about, machine learning, because AI has multiple, repercussions. It can be used by everyone on anything and everything. But specifically, when you talk about machine learning, so you can use machine learning along with simulation models for plenty of things. For example, you can take a very complex CFD or an FEM model, and using neural net, if you can get a reduced order model for that. So that can be very lightweight, which can be used much faster. Here, in this case, what they are doing is whether a particular aircraft is controllable or not. So that they are trying to, instead of controller, they have this neural network, and this neural network they kind of tune and see whether it can be controlled, whether the system is, controllable. Similarly, there are other, so this is another case where they take actual system, perfect the model, and once the model is perfected, they give it to, let us say, it's called design selection. But actually here on optimization happens. So they optimize to make sure the aircraft properly takes off and does not have a failure. So through real-time optimization that they do. So again, just to close this section, what I would say is there are types of simulation and things are growing. So we need to keep abreast with what is happening in the field. So far, any questions, or I'll move ahead? Okay. I think I'll move a little fast, because at least at the last you should have some options to. There should be some time for asking questions. So system simulation, it is all purely physics based, and I can give you a quick example. Let us say we want to model the aircraft cabin volume. So we can go with ideal gas equation and model it, right? So that is lump parameter. We consider that as an entire volume and we model it, so that we'll know what is the temperature provided, what is the airflow in, at what temperature the environmental control system is supplying this air. And all of these are known. So with pure simple physics, you can model this whole thing. So that is system simulation. And when we go to 3D simulations, I would say both CFD as well as FEM is all about going from continuum to discrete. So how you discretize, and at those discrete points, how you solve. So maybe in fluid mechanics, CFD, I think Jay is here, so he knows much better. But the Navier-Stokes that you solve for each of these grid points, you can get all the variables of interest. Similarly, on the FEM side, Hooke's law is there, and stiffness matrices and everything you consider. And at the discrete points, once you perfectly define the geometry as well as you're able to mesh the geometry, right? Because you need to get all these grid points where you want these equations to be solved for. So once this is known, then we can actually do that. So you need fundamentals of fluid structures, and also numerical schemes are something that you should be aware of. So I'll run through the simulation tools. I basically, because I don't want this lecture to be about, commercial softwares and other things, but just for your information, I think when it is the FEM, people talk about ANSYS a lot, COMSOL, Altair as a tool. For CFD, again, Fluent is there, OpenFOAM is open source, and SimScale is also big there. For requirements, Doors is from IBM, I think, and Cameo is also available. And for system simulation, AIMSIM, Simulink, Modelon Impact, Dassault Systems, Daimola. So these are all different tools that are available in the market. Opportunities. I think aerospace simulation, again, I want to clarify here, there are plenty of things that an aeronautical engineer can do. But here we are talking about simulations in particular. So when it comes to simulation opportunities in India, within the government sector, I think DRDO, ISRO, HAL are there. But I think I won't say there is plenty of opportunities there, but definitely a lot of simulations happen there. Then all these global capability centers, for example, Boeing, GE, Honeywell, Collins, Rolls-Royce, and there are even other things in India. So these global capability centers, they use simulations extensively, and their main aim of coming to India to start these GCCs is because in India they can get simulation engineers more in numbers quickly. So that is their main interest point of interest. Then I also see a lot of these startups, and for startups, as Jay mentioned, everything has to be fast. They want to go to the market fast. So they also use a lot of simulations, Skyroot, Agnicol, Cosmos, all of them, they use simulation softwares. And engineering service sector, this is always there. I think CR, L&T also takes up a lot of aerospace projects. So they basically take simulation projects for companies like Boeing and others, and they execute. So there are also simulation requirements are there. Then finally, if someone is interested in simulations and work for simulations, they can as well go and work for a simulation company, right? A company which makes the simulation software, Dassault, Altair, MathWorks. So I would say there are plenty of opportunities. No need to worry about simulation being a narrow field. And I'll go to the next one. So when it comes to engineers, I would say there are two types of engineers. I think dynamic engineers and transactional engineers. For dynamic engineers, you need abstract thinking. Any complex problem is given to you, how quickly you understand and you're able to abstract things, right? I mean, how you are able to bring clarity to a complex problem. Then problem solving, and how you can work well with team. And also how you can work well across international borders, how you can work with people from other cultures. You should have strong interpersonal skills. So these qualities make a dynamic engineer. Then there is a transactional engineers. I mean, you have good engineering fundamentals, but you can do repetitive tasks, but you cannot solve bigger problems. So the industry is definitely looking for dynamic engineers all the time. So what does industry expect? Good science and math background, a bit of programming. You have to be a quick learner because you cannot define industry. You cannot say this is where industry is and this is where industry is going to be. Things are changing fast. So we need to be a quick learner. So possible industry experience, I think it is meaningless, but my point is, if you, within the 4 years of your study, if you had a chance to be with some industry or solve some industry problem, right? So that is being valued quite heavily. You have to be a team player, you have to be time conscious, open-minded, action-oriented. So this is something which I picked from Copilot, the skills required. So you can clearly see the tools, the programming, domain knowledge, what domain knowledge is required, soft skills. So simulation as such is not going to bring you any value. When you have the fundamentals along with simulation, then it kind of adds a lot of value to you. So now the question is, what action should I take? Basically, I want to keep some time for questions or discussion. That's why I'm rushing through. We are near the 1 hour mark. So you have to enhance your knowledge and skills, fundamentals, problem solving, tool expertise, communication. So all these things you need to improve. And mini projects, how many mini projects you can do, right? So you can get the problem definition and guidance from alumni like us. Or I also see that MIT works with industry academia partnership. I keep seeing somebody from Boeing visited us today, somebody from Rolls-Royce visited us today. All these LinkedIn messages I see. I think you should talk to them and say, like, can you give these small problems that we can solve using these simulations? Then thesis or your project, right? I mean, keep the entire last semester free, because most of the companies prefer having the person doing the project for a 6 month period, the entire 8th semester uh, in the company. So that can also increase your chances of getting this industry experience. So push the department, push the HOD, and to get these mini projects and thesis from industry as they keep talking to industry. And as students, you can be pretty active in associations like SAE and INCOSE. INCOSE is an association which works strongly on systems engineering requirements or system simulation. SAE, I see them conducting all these events, not only for auto, but also for aero. So that also can, give you a lot of experience. Yeah, I think I stop here. Maybe open for floor for questions.
Good evening, seniors.
Good evening.
Good evening.
On behalf of all the students, I extend my heartfelt gratitude to Anand Senior and Jaykumar Senior, and to all our seniors of the 49th batch for organizing such a wonderful session. Your time, effort, and valuable insights have truly inspired and guided us, and this session will surely help us in our journey ahead. Sincere thanks to one and all present here. Thank you, seniors.
Yeah,
Thank
thank
you.
you.
Thank you. Bye.
Yeah.
Thank you. Thank you.
Bye.
Bye.